Hi, welcome again in the course of Control Theory MA3005. We are now in the third session, which will discuss on mechanical systems. As the learning objective of this topic, by the end of this topic, you should be able to derive dynamic model of any mechanical system. Okay, when we are talking about mechanical systems, we always deal with three main elements. The first one is inertial element. It's a mass. If we are dealing with a translational system, it is a moment of inertia. If you are dealing with rotational system, the second element is spring. One thing that we have to underline here, if you have a spring, the unique property of spring is that the spring will deform by an external force where the deformation is proportional to the force that you apply to it. Of course, when you are dealing with rotational system, you will apply a torque. So the deformation will proportional to the torque in a case of rotational system. The last element is damper. Damper is pretty similar to spring, but in this case, the force that applied to the element is not proportional to the deformation, but instead the rate of the deformation, or in other words is the velocity. Again, of course, if you are dealing with rotational system, it's the angular velocity. Let's take a deeper look on the spring element. Any spring always has a property that is called as a spring constant, or sometimes we call it also as a stiffness. And stiffness, you can use a notation of K. Normally we call it K as a spring stiffness. Now let's take a look to this following animation. Imagine I have a spring, okay, and then I hold this spring at the two ends with my two hands. My left hand is holding the left end of the spring, my right hand is holding the right end of the spring. And then I stretch this spring. So I move my left hand to the left, my right hand to the right. In this case, of course, if I move my left hand to the left by x1 in and my right hand to the right by x2, the total deformation of the spring will be x1 plus x2. So the total deformation of the spring is x1 plus x2. Now let's take a look what happened to the force that is applied to the spring. Let's take a deep look again on the case that we just discussed before. We have a short live demo that I will share it with you. So here I'm taking the same spring. So let's say this spring has a spring constant of K, and then I'm holding this spring, and then I will stretch it. My left hand, I will move it to the left, and then my right hand, I will move it to the right. So this spring will be stretched from the initial position. I will stretch it like this. The relative deformation of the spring, of course, will be equal to x1 plus x2. And this means I applied my hands, applied a force to the outward direction of the spring, where the applied force is equal to K times x1 plus x2, proportional to the relative deformation. But now, let's imagine what I feel. When I stretch this spring to the outward direction, I pull it to outward direction, I have a notion, I have a feeling that the spring is trying to pull my hands, both of my hands, back to the inward direction. This is because of the reaction force from the spring that is applied to my hands. Okay? Now let's go back to the slide. Okay, from what you have seen from the previous small experiment, if we have a spring and then we stretch this spring by pulling it in the outward direction, technically then we apply forces in the outward direction to the spring, where the force is proportional to the relative deformation of the spring. But our hand, which pull this spring to the outward direction, as a consequence, we'll have a notion that our hands is pulled back to the inward direction by the spring. This is just the action-reaction law from the first Newton law. Okay, so if you pull the spring to the outward direction, your hand will have a feeling that the spring is trying to pull your hand back to the inward direction. In the previous examples, we take a look on the application of the translational spring when we stretch it. Okay. Now let's take a case when the spring is compressed. Saying that if you have a spring, the left end of the spring is pushed to the right, this one, let's say by x1, and the right end is pushed to the left by x2. What will happen? Of course, the spring will be compressed. The force that is applied to compress the spring, similar to the previous one, is proportional to the relative deformation. Since the left end is pushed to the right by x1, the right end is pushed to the left by x2, so the relative deformation will be x1 plus x2. That means the force applied to the spring is in inward direction because we compress it, and the force is equal to k times the relative deformation, x1 times x1 plus x2. Okay, so F is equal to k times x1 plus x2. And then what happened to our hand that compressed the spring? So imagine again, both of my hands are compressing the spring, okay, because of the reaction force from the spring. My hand, I will have a notion that the spring is pushing back my hand to the outward direction like this. So it's just a action-reaction problem here. I have a notion that my hand is pushed back by the spring in the opposite direction. This is the reaction force to my hand because of the spring. Now, let's take a look another case now when we have a rotational spring. Let's pay attention on the live video that I will show you after this. Okay, in the previous slides, we discussed about the behavior of translational spring. Now let's imagine we have a rotational spring. So let's imagine you have a shaft like this, but imagine the shaft is rather flexible here. But before we discuss about the rotational rotational spring, let's discuss first the common notation about the rotational spring. So for the notation of the direction of this rotational spring, in the drawing, if the spring is rotating in this direction, okay, in this direction, I will notate it with a clockwise arrow as I indicated in the drawing. If this shaft is rotating in this direction, okay, I will put a notation with a counterclockwise arrow, okay. Now let's imagine my left hand will twist this shaft in a clockwise direction. So my left hand will rotate it in a clockwise direction like this, and my right hand will twist the right hand to the counterclockwise direction, which means I will squeeze this shaft, I will twist it like this, okay. My right hand is rotating in that direction, my left hand is rotating in this direction, so I squeeze this shaft like this. What does it mean? This means to this shaft there is a relative angular displacement. If I twist the left end of this shaft in a Q1 with a direction of clockwise direction, Q1, and my right hand I rotate it in a counterclockwise direction about Q2, the relative deformation, the relative angular deformation of this shaft will be Q1 plus Q2, okay. And then because of the Newton law, it says that the similar to the translational spring, the force acting on the springs will be proportional to the relative deformation of the springs. In here, it's also the same. The torque applied to this shaft is also proportional to the relative deformation of this rotational spring. So if I twist it like this, my left hand is rotating Q1 in the clockwise direction and my right hand is rotating Q2 in the counterclockwise direction. The torque that I applied to this shaft is proportional to Q1 plus Q2. Let's take a look on the slide after this. Okay, as what we have already discussed in the live video that you have seen before. Again, if I have a rotational spring, as you can see in this drawing in the left side of this slide, as indicated in this drawing, the left end of this shaft is twisted to the clockwise direction and the right hand is twisted to the counterclockwise direction, which means to the shaft we have a relative deformation. To be precise, we have a relative angular deformation which is equal to Q1 plus Q2, right? What does it mean? This means to this shaft, to this rotational spring, there is an applied torque to twist the shaft in this direction. It's similar to what we have discussed in the live video. And the torque that is applied to this rotational spring, again, similar to the translational spring, the torque applied to this spring will be proportional to the relative angular deformation Q1 plus Q2. So the torque here, I indicated as T here, is equal to K times Q1 plus Q2. Again, of course, here is similar to the translational spring. K here is also the spring constant, but of course, what we have here is a torsional spring. Okay, so those are the properties of spring. As we discussed before, there are basically three elements in mechanical system: spring, damper, and mass. In the next few slides, I will discuss about the property of a damper, the second element. Okay, this drawing illustrate the second element, translational damper. Let's just consider a translational damper here. The behavior of damper is pretty similar to spring. So if you still remember in the previous two slides, we discussed about translational spring, in which the force applied to the spring is proportional to the relative deformation. For damper, it's pretty similar but not exactly the same, because in damper element, the force applied to this element is not proportional to the relative deformation, but instead it is proportional to the rate of deformation. So it depends on how fast you compress it or how fast you stretch it. Depends on the velocity, on the rate of deformation. So as illustrated in this slide, I have a damper with a damping constant of B. The left end of this damper is pushed to the right with the rate of deformation of x1 dot. Dot here indicates the first derivative of deformation. So x1 dot represent the rate of the deformation, the speed of the deformation, how fast we push it to the right side. So again, the left end of this damper is pushed to the right side with a speed of x1 dot. And then on the right side, we pull it to the right direction as well with a speed of x2 dot. So because both of them are moving at the same direction, if we know that x1 dot is greater than x2 dot, the relative deformation, the relative rate of deformation will be x1 dot minus x2 dot. So the force that is applied to this damper is proportional to the relative rate of deformation, x1 dot minus x2 dot, which is equal to B times x1 dot minus x2 dot. Okay, direction wise is pretty similar to spring. The only difference in here is only the norm of the force. It's not proportional to the deformation, but it is proportional to the rate of deformation. To illustrate it more clearly, you can take a look on the animation of this damper. Similar to spring, we also have rotational damper. So again, like what we discussed in a rotational spring, we take the same annotation here. Clockwise is rotating in the direction that I have already indicated in the rotational spring live video in the previous few slides. And then as well as counterclockwise, we have the same annotation there. But for rotational damper, it's similar also to translational damper. The torque applied to this damper is not proportional to the deformation, but instead is proportional to the relative rate of deformation. Direction wise is again pretty similar to rotational spring, but of course here the only difference is that torque here, the applied torque here, is proportional to the rate of deformation. One thing that you might want to indicate here, B here of course is the damping coefficient, but it is for torsional system. So B here indicates torsional damping coefficient. We have already discussed two of the main elements in a mechanical system, spring and damper. The last one is the mass. it's a mass for translational system, and it is a moment of inertia for rotational system. So when we are going to develop a model of a mechanical system, we only have one and only tool to derive the mathematical model of this mechanical system. The only tool that you need is the Newton's second law. The Newton's second law is derived from the property of the mass for translational system, of course, and it is a property of the moment of inertia if we are talking about rotational system. What Newton's second law says is that total forces acting on a mass will be equal to the mass times the acceleration. That is for translational system, of course. So the total forces acting on the mass will be proportional to the mass times the acceleration. For rotational system, the total torque acting on the moment of inertia will be equal to the moment of inertia times the acceleration in the rotational direction, of course. So the total torque will be equal to moment of inertia times rotational acceleration. So this is the only tools. What you need to do then, you have to derive all of the forces from the spring and damper element, and then you consider the forces on the mass. After that, you use this Newton's second law to derive the model. In the next slides, I will give the illustration on how to derive the mathematical model of a mechanical system using all of the properties that we have already discussed.